In this video, we're going to go over stereochemistry, which is a branch of chemistry talking about the 3D structure of different organic molecules. So an isomer is something that has the same molecular formula, but it's somehow different. Okay, so a constitutional isomer might be this guy, which is C1, 2, 3, 4, 5, 6, 7. C7, H some number, and then OBr. This guy right next to it is actually also the same thing. And so a constitutional isomer is something where the atoms are bonded in a different fashion. A stereoisomer is actually the same exact compound in terms of how it's bonded. So we might have something like this. And these could be stereoisomers, but they have a different 3D arrangement. So for example, and you've probably seen this throughout organic chemistry from time to time, maybe that bromine is on what's called a wedge, and then maybe this bromine is what's on a dash. And we're going to talk about what that means in terms of the different 3D structures. Now, why does stereochemistry matter? Well, turns out that molecules, just like your hands, there could be a right hand and a left hand, and maybe only the right hand is the perfect shape and the perfect orientation to work for a specific mechanism. So for example, this came up with thalidomide, which was an anti-nausea medicine that pregnant women commonly would take to cure morning sickness. Now, the thing is that when you make thalidomide, you get the anti-nausea medicine, but you also get its enantiomer. And we're going to talk about enantiomers later in this note, but let's just clear this up right now. An enantiomer is a mirror image. Okay, just because it's a mirror image, that doesn't, even though it may look very, very similar, that doesn't mean it is. Just like your left hand may look very, very similar to your right hand, but they cannot be superimposed on top of each other. And the enantiomer of the anti-nausea medicine actually happens to be a teratogen, which is something that causes some sort of malformation like a birth defect. And so a lot of babies around this time were actually born without limbs. And there's still people to this day that are living with the effects of thalidomide. So stereochemistry is actually a huge part of organic chemistry that we've sort of ignored up to this point, but now we're going to take a closer look. Maybe something that you have experience with would be ibuprofen. So these guys are mirror images. Okay, these are enantiomers. And actually, one is called the R enantiomer, and that's part of ibuprofen, and it's inactive. And then there's the S enantiomer, which is actually 160 times more active. So that would definitely be the type of ibuprofen that you want if you're in search for some sort of pain relief. Okay, so wedges and dashes, these are really, really important. So wedges represent a bond that is coming towards you or out of the page. So if we have something that's like this, if you draw this on your paper and that's a bromine, let me move that down a little bit. That bromine would be pointing out at you. Whereas dashes represent a bond that's going away from you. So if we draw the same molecule, these actually happen to be enantiomers, that bromine is pointing into the paper, okay, or onto your desk or wherever it is that you're writing. This is really important, and I'm going to highlight it in orange because it's so important. On a single carbon, you can only have one wedge and one dash. And I know that that's going to be a little bit misleading with some of these structures that you see, but the way that we are going to draw them to make sure that we're 100% correct is that you can only have one wedge and one dash on each carbon. Now, wedges and dashes are typically only used to distinguish between different groups on a carbon center. So for example, if we had another bromine on that carbon, on each of those carbons, they would essentially be the same thing as this. You wouldn't actually probably use stereochemistry unless you had different groups, and we'll talk about that in terms of something called chirality, which is maybe something that you've heard of before. So, for example, even though one of these hydrogens is wedged and one of them is dashed, we're probably not going to draw them that way unless they were different groups. Okay, so a chiral center, or something that is chiral, that means that we have all four substituents or groups coming off of our central atom are different, okay? When this happens, this carbon is going to be called a stereocenter or a chiral center, and we're going to see that with some examples here just in a second. And then if something has two equivalent groups, like here, that would not be chiral. That would be actually achiral. Okay, so how do you even identify a chiral compound? Well, first of all, a chiral compound needs at least one chiral center. And what will happen is we've got to be able to master that definition of chiral center. But what you'll see is that just because we see wedges or dashes here, that doesn't mean that each of those groups is actually a chiral center. The reason why is, even though on something like this, it would be ridiculous to focus on the stereochemistry, it still is a 3D structure that does have stereochemistry. It's just that for convenience, we only draw stereochemistry when it's actually useful to us. Okay, so what I want to do is I want to mark each of these carbons, and we're going to look at them and ask ourselves, does that carbon have 4 different groups? So on this first carbon, does that carbon have 4 different groups bonded to it? It has this group, whatever you want to call this group coming off of it, and then it's got 3 hydrogens. Okay, so that is not a chiral carbon. Okay, does this second carbon have 4 different groups? It has 2 hydrogens, so no, it is not chiral because it does not have 4 different groups coming off of it. Does this middle carbon have 4 different groups? Well, one of its groups is an ethyl, one is a methyl, one is an isopropyl, and then the fourth that we can draw in here is a hydrogen. And so yes, that does have 4 different groups. And so I'm going to box this, and I'll keep that hydrogen there. That is definitely a chiral carbon. Okay, does this bottom carbon have 4 different groups coming off of it? The answer is no, because we have 3 hydrogens. Okay, does this carbon that I just circled, that second to last carbon almost, is it chiral? A lot of people would say, well, there's a wedge on it, so it's got to be chiral. But the answer is it's got one group, whatever you want to call this, a sec-butyl group, I guess, on it. It's got a methyl, and then a dashed hydrogen. But since it has 2 methyls, it's actually not a chiral carbon. Okay, so that is not a chiral carbon. And then these methyl groups, a methyl carbon will never be chiral because it'll have 3 hydrogens. So this compound actually only has 1 chiral center or stereocenter. Okay, so I'm not gonna write this out, but I'm just gonna talk through it, why the highlighted area represents the only chiral center on each of these 3 molecules. So what you wanna do is we wanna say, okay, if there's a wedge, then there's also gonna be a dash, and if it's not drawn, then the dash must be, a hydrogen. We have a chlorine, a hydrogen, an ethyl group, and then a methyl group. That would be 4 different groups, so that is true. This is the only chiral center. Here we have an alcohol group, that's 1 group, a hydrogen, a propyl group, and then an ethyl group, so that's 4 different groups, so that means that is definitely chiral. And here's what's really interesting. I want to compare this compound with bromine versus the same compound with no double bond. We have a bromine, and we have hydrogen, so one group, two groups, and rings just always kind of take a second to get used to. So here's what I want to think about. We could go around the ring to the left, or we could go around the ring to the right until we collide at this bottom carbon. So if we go the left route, will it look identical as the right route? If so, that left route and right route are not actually different groups. So here with this bromine, this has no chiral centers, where with the double bond, my left versus my right has a double bond, and that differentiates itself from the left side, okay? And so that's what makes that actually a chiral center. So what we're gonna do is I wanna practice some of these. I'd appreciate it if you would pause the video. I'm gonna go through this but quickly, so when you're done, you might just need to put me on double speed for a little bit as I go through this so you can check. Okay, so go ahead, pause this, find each chiral center and just box them. Okay, so not chiral, those are methyl groups. Okay, so those cannot be chiral because they have three hydrogens. This group looks chiral, but it's not because we have methyl and methyl. Okay, so we need 4 different groups. When we go here, this group is chiral. The reason why is we have a sec-butyl, we have a methyl, we have an isopropyl group, and then we have a wedge hydrogen actually. Okay, this group is also going to be chiral. The reason why is because we've got 4 different groups. If I erase everything here, we've got a methyl, an ethyl, and then whatever you call this, and then a dashed hydrogen. So that allows it to have 4 different groups. And then this carbon is not chiral because we have 2 hydrogens attached to it. Okay, looking at this second one, methyls cannot be chiral, so I'm just going to go ahead and cross those out. That really helps me out here. Now, also, to be chiral, you need 4 groups. So this carbon and this carbon on the double bond, they're actually only bonded to 3 groups, and I'll highlight that. So for this top one, we have a methyl, we've got whatever this is, and then the rest of the molecule. That's only 3 groups, and so you have to have 4 groups to be chiral. So we're not looking there, we're not looking there. We've got these 3 carbons left. This one has 2 hydrogens, so that's not chiral. Let me erase this to make it a little bit cleaner. This carbon is chiral and this carbon is chiral because when you go ahead and you count it up, they each have 4 different groups. So the thing that's nice is I see 2 hydrogens can't be chiral. Methyl can't be chiral, but this guy has methyl, hydrogen, chlorine, and then whatever you want to call that group. So that is definitely a chiral carbon. Now, what's a little bit tricky on this one, methyl, 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 2 hydrogens, 2 hydrogens, 2 hydrogens, none of those groups are chiral. Now, if I look at the central carbon, do I have 4 different groups there? I have an ethyl group, an ethyl group, and an ethyl group, so the answer is no. This has no chiral centers. Okay, now let's look at this ring structure. Rings are a little bit tricky. Okay, so methyl, 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 no chiral centers. This carbon has 2 methyl groups coming off, so that's not chiral. This one has 2 H's, so that's not. This has 2 H's, that can't be. H and H, so that can't be. So now we're left looking at these 3 carbons, okay? I'm not saying that they're chiral, I just gotta evaluate them. So if I travel the top way versus the bottom way, will the ring look exactly the same? Well, the top way surpasses or passes, I should say, an alcohol group, so it is different than the bottom way. So that means that this carbon is in fact chiral. The same thing is here on this alcohol carbon. This is a chiral carbon. The reason why is when I go left, that looks a lot different than when I go right. The reason why, that when I get to my first carbon going right, I've already hit an isopropyl group. I did not hit an isopropyl group on my left way on the first carbon that I hit. Okay, now what about this last one? Again, if I go top versus if I go bottom, I'm going to hit the alcohol on the top method, and so that means that that is a chiral center. Okay, last one. This carbon is not bonded to 4 different groups. This one's a methyl, so we can't say. This carbon is chiral because if you count, we've got 4 different groups. Even though I didn't draw any stereochemistry, we've got carboxylic acid, we've got an alcohol, we've got a methyl, and then we've got a hydrogen. And I didn't draw the stereochemistry, but you know, maybe that one's a wedge and that one's a dash. Okay, I'm going to go over Miso compounds just quickly. These will not show up on the test, but they would show up if you are in college level chemistry. So a Miso compound is a compound that has 2 or more stereocenters or chiral centers, but they have an internal mirror plane that actually destroys its chirality. So both of these are chiral centers with those fluorines. But what happens is with this mirror plane, that actually just cancels everything out, okay? So, which of the following structures are Miso compounds? Well, to be a Miso compound, you need at least 2 stereocenters. So A is not because it has no stereocenters. On B, we do have 2 chiral centers. However, there's no internal mirror plane, and the reason why is that in this top structure, if one side folds onto the other side, we'll get the same structure. On B, chlorine, if it folds onto fluorine, it's not going to be the same, okay? So this has no mirror plane. Here is a stereocenter, and here's a stereocenter. Don't worry about these 2 carbons having double wedges. This is a whole different branch of organic chemistry that we haven't covered yet with this. These are very weird structures. Don't worry about that so much here. If I divide it this way and they fold on top of each other, this is a Miso compound, okay? Because if this top part folds onto the bottom part, they will be exactly the same. Okay. Chiral centers, and this is what I call a double Miso compound because we could fold top to bottom or left to right. Here we have a chiral center, but we don't have 2 chiral centers, so there's no way that this could be Miso. Additionally, you may say, what about this carbon? That's a methyl group, and this one's drawn as CH3, still a methyl group though, so that's not 4 different groups on that carbon. And then here we have a chiral center and a chiral center, and there's no way that they can fold on top of each other to actually get them to line up. Okay. So now what I want you to do is I want you to pause the video, identify all the stereocenters on the following molecule. This is a huge molecule. This is what if you go into biochemistry, you will start to study molecules that look this big. This is specifically called Taxol, and it is an anti-cancer molecule that is used against leukemias or different tumors in the breast, ovaries, brain, or lungs. And was isolated from the bark of some Pacific tree in 1971. A lot of organic molecules have a super interesting history. So go ahead, pause this. I'm going to just give you the answer when you unpause it. So go ahead and pause it now. this carbon, let me make sure I didn't miss any. Okay, I think that's good. Okay, now we're going to do the same thing here. Rifampin. Okay, let's draw these chiral centers. So go ahead, pause the video and see if you can find all the chiral centers. Again, that's where carbon has 4 different groups attached to it. There's one. There's one, there's one. There's one, there's one. There's one, there's one. There's one. Let me check the rest of these. I can quickly pass over double bonds because I know that those can't be chiral, and I can quickly pass over methyls. I think that's all of them. Now, here's how we're going to draw enantiomers. One thing you could do, and by the way, enantiomers, we've talked about it, those are mirror images, is you could literally get your phone with the screen turned off and put it up next to, you know, right here, and you could see the reflection, or actually get a mirror, and you could see that the reflection, if you draw this, looks like this. This is an enantiomer. But what's an easier way to draw an enantiomer without having to think so much about it is to get an enantiomer, all wedges go 2 dashes, and all dashes go to wedges. Okay, so here's the way I kind of like to do it, is I draw the same structure, but to get the enantiomer, I just turn that wedge to a dash. And believe it or not, if you took that molecule and you flipped it, like physically just turned it 180 degrees, it would be that molecule. Okay? If we were in class, we'd be able to see this very easily, but sadly we're not. So again, an enantiomer, what I would do is just, that alcohol group was a wedge, so I'll make it a dash, and that bromine group was a dash, so I'll make it a wedge. Okay, so go ahead, pause the video, get the rest of these drawn, and then we're about wrapping up here. Okay, now diastereomers. Diastereomers are going to be a compound where there at least one stereocenter is flipped, and I'll talk about what that means in just a second, but not all. Okay, so let's see what this might look like. Let's say this is what we have, a wedged alcohol group and a dashed methyl group. If I drew an enantiomer, I would get a dashed alcohol and a wedge methyl, okay? And that shouldn't be too bad. But what a diastereomer is, and I'm going to abbreviate that, and very common in organic chemistry to abbreviate enantiomer E and diastereomer E. What a diastereomer is what if you just flipped one of them, like this alcohol group, and you left the methyl group a wedge? And that would mean that what we've done is that we've at least changed one of the stereocenters, but we didn't do them all. If we do them all, it's an enantiomer. But if we just do one, it's a diastereomer. Okay, so here, if we wanted to draw another diastereomer, we could draw, let's see, a wedged alcohol group and a wedged methyl group. That would cause these guys to be enantiomers down here. And then these guys would be diastereomers, and then these guys would also be diastereomers. Okay, now the last thing I want to go over, and I'm going to flip back to earlier pages, is that how many different configurations can you obtain if you have more than one chiral center on a molecule. And it's actually a pretty nice formula, and it's just 2 to the power of the number of chiral centers. So this compound has 2 chiral centers, and I'll box them for you. If I want to know how many different structures I can draw that are considered stereo structures or stereoisomers, I do 2 to the second, which equals 4. If we go up to where we were practicing, all the way up here, this guy has 2 to the second, which equals 4. This guy has 2 to the second, which equals 4. This guy has 2 to the first, which equals 2, which means it doesn't have any diastereomers, I flip 1, and by default I flip them all because there is only 1. This has 2 to the 0, which is 1, which means it only has one possible structure. This guy has 2 to the third, which is 8. And then this guy has 2 to the 1, which is 2. So it may seem like that's not a very important formula, and it might not be under a lot of circumstances, but what it gets you is we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. We have 2 to the 11th, so the number of different 3D structures we could draw here, let me get this, 2 to the 11 is 2048. And that would be by drawing every Miso, each compound, not Miso, but drawing the enantiomer and then drawing the diastereomer, one diastereomer. We have lots of different diastereomers here. What's kind of interesting is if we have 2 to the 11, we have one enantiomer. Well, you can only have one mirror image. We have one original compound, and then we have 2048 minus 2. We have 2046 diastereomers. Okay, so that's it for notes 1.